So the title of my talk is Spandex, a flexible interface for efficient heterogeneous coherence. This is joint work with my former students, Jonathan Alsop and Matt Sinclair. Matt is here somewhere in the audience. John is at AMD now, and Matt is a professor at Wisconsin. Okay, so this work is actually in the broader context of memory system design for heterogeneous computing. Matt is going to give another talk in our larger project tomorrow, so a plug for his talk. I'm going to focus on one narrow aspect here. Okay, so specialized architectures, heterogeneous computing is becoming increasingly important in all sorts of computing domains, ranging from IoTs to data centers to supercomputing. One of the key challenges to get performance out of specialized heterogeneous systems is to design good memory systems. Right? So traditional model of heterogeneity, the conventional thinking is that you have a CPU host, and that host it offloads some computation to the accelerator, it generates some data, sends that data to the accelerator computes on the data, generates some data, and that data gets transferred back to the CPU. So this is quite inefficient, in particular if you have any kind of fine-grained synchronization, irregular communication in your code, or a communication that requires some runtime on-the-fly knowledge. This becomes inefficient because you don't really you have to a priori figure out what data needs to be communicated, when it needs to be communicated, et cetera, and before you send it to the accelerator. And it is wasteful in terms of the data movement. So instead, we've seen a movement now towards heterogeneous systems that employ shared memory, and in particular coherent shared memory, where many of these problems get eliminated because you have a uniform memory space between the CPU and the accelerator. You can do fine-grained synchronization, irregular access, and you have implicit data reuse across this common memory system. However, maintaining this vision of illusion of of a coherent shared memory space is quite complex, and the existing solutions are complex and inflexible. So why is that? Well, a key problem with heterogeneous systems, unlike the previous world of CPUs, is that these devices are specialized for specific data access patterns. Right? The whole point here is specialization. And so they're trying to deal with workloads. Some workloads might have spatial locality, some might have temporal locality, some may have fine-grained synchronization, some may be latency sensitive, some may be throughput sensitive, and they all want to, so to get the best performance, to get the best specialization, you want to specialize to each of these types of systems. So a typical CPU workload, for example, might exploit fine-grained synchronization and be latency sensitive. GPU workloads, on the other hand, exploit spatial locality and are throughput sensitive. And because of this reason, the types of coherence protocols that you want to run on each of these accelerators for best efficiency are different. Okay, so we've looked at a range of access patterns, and we narrowed down to these three axes or dimensions for different coherence protocols. So the first one is granularity. At what granularity are we doing our accesses? For CPU workloads, the commonly used family of protocols that you're all familiar with, like MESI or MESI, they use line granularity. So cache line granularity is 64 bytes, for example. This is good to exploit spatial locality. The problem is you can have false sharing. The second dimension is that of invalidation of stale data in the cache. So typically, CPUs use writer-initiated invalidation, which means that the read reads the data, keeps it in the cache, and the next time a write happens somewhere else, that writer is responsible to go and invalidate the data in other caches that has now become stale. So this is great because now the reader can keep the data for as long as it wants to until the next write happens, and it works great when you have temporal locality for reads. The problem is that when the write happens, it has to go about sending these invalidation messages, collecting acknowledgements, which is extra overhead and limits throughput. For updates, that's the third dimension. What happens on a write? So the CPU-style MESI protocols require getting ownership on a write. So the cache that does a write gets ownership, and now it keeps that write data in its cache until somebody else wants to write and grabs ownership away from it. And this is great when you have temporal locality for writes. However, if there is low locality, then somebody who wants to read this data needs to come all the way to your cache to grab the data from you so that it can take away ownership from you. And so that is a level of indirection that you paid the price now. Okay, so, but this works great for CPUs because it maps really well to generic CPU workloads. With GPUs, we have a different set of trade-offs. So on these dimensions, if you look at granularity, GPUs read at line granularity, but they typically write at cache word granularity. So this is great because there's no false sharing because you're writing at the word granularity. However, these word-based writes need to be sent out to the next level of the cache hierarchy at synchronization points, limiting spatial locality to synchronization points. For invalidations, what GPUs do is the reader takes a charge of invalidating itself. So the reader says, at the next synchronization point, I'm going to self-invalidate my cache. This is great because there is no overhead at all. Okay, no extra outside invalidations, acknowledgements, etc. Very simple, but the locality is limited. The reuse is limited to synchronization points. Okay. For updates, GPUs do write-through, so they don't get ownership, and the write-throughs need to be sent and made sure that they're done at synchronization points. So again, simple, low overhead, but heavyweight stuff happening at synchronization points. So this worked great because GPU workloads were coarse-grained, synchronization happened rarely, and this was just a fine trade-off for those types of workloads. Okay. DeNovo is a protocol that we developed in my group and showed that it hits a sweet spot between CPUs and GPUs. So DeNovo, the read granularity is flexible. It can be word-based, it can be line-based, it can be multiple words in a line. For invalidations, we use self-invalidates. For updates, we use ownership-style updates. And we showed that this is a good sweet spot. So the point of this slide is there's lots of things, lots of different options, lots of different ways in which you can build protocols depending on your system or your workload. So now the question is, okay, how do we put devices that might have these different protocols, how might we integrate them together in a given system? Okay, so I'm a system designer. I get accelerators from different vendors or even from the same vendor for different parts of my kernel, different kernels of my application. They're all wanting to use different protocols. How do I put them together? Okay, so today, this integration is quite expensive. In particular, the standard sort of temptation is to use CPU-style protocols at the last level of your cache hierarchy to integrate all of these devices. And this is partly because we are familiar with these CPU MESI-style protocols. So for example, if I have a device that already does MESI, this is awesome. You just connect it to my last level cache. But I might have a device that doesn't do MESI, and one way of integrating it is to say, well, all the accelerator loads and stores are going to be non-cacheable. I'm not going to allow you to cache because you don't follow my MESI protocol. Another option might be to say that, well, I don't care. I will let you cache, but you have to now implement MESI. I'm not giving you a choice. And a third option, for example, AMD APUs, you put in another hierarchy, another level of the cache in the system so that this in-between hybrid cache can filter the accesses from the GPU in this case so that that filtration then matches the GPU, whatever comes out of the GPU, it matches it with the MESI protocol. Okay, but all of these styles incur some form of overhead, either in implementation, performance, or efficiency. So our proposal, our work is called Spandex, and the idea here is to provide a flexible heterogeneous coherence interface that can essentially adapt to the needs of whatever protocol the accelerator devices want and allow these devices to integrate together without really pushing anything else on top. Okay, so if you have a CPU with MESI, Spandex adapt, you can have an accelerator with GPU-style coherence, you can have an accelerator with DeNovo-style coherence, and Spandex will adapt to that and allow you to connect these devices directly together in this integrated last level part of the hierarchy. Okay, so the idea is that it gives better performance, lower complexity by exploiting individual devices' workload attributes, and fits like a glove for any heterogeneous system. Okay. All right, so what is Spandex about? How do we actually achieve this? There are a few components to Spandex. The first one is the device request interface. Okay, so what kinds of requests do we expect these devices to make? The second is the last level cache, which is based on the DeNovo protocol that my group has been developing over the years. The third is the external request interface. So each device or some devices might need to deal with some external requests that the LLC generates. So how does it do that? Well, that's the third part. And finally, some devices, not all, but some devices may need a thin translation unit to translate from whatever they have into what Spandex expects. Okay, so I will talk about that. All right, so let's start with the flexible device request interface. Here we have, for read requests, Spandex has two different types of reads. One is a read that says that it's going to take care of the invalidations itself, so it's read with self-invalidation. We support read with writer-initiated invalidations. Writes can be write-through, or writes can be with ownership only. And then we support read modify writes. Again, you can have atomic write-through or atomic accesses that get ownership with data. Okay. Finally, you have write-back caches to do write-backs. All right. So these requests also additionally specify a granularity, including potentially a bit mask that tells you which words in a particular cache line you want this request to deal with. Okay. Another key thing is that all of these requests can be mixed and matched in the same program in the same device if the device wants to support them. Right? So it's completely orthogonal and composable. Okay, so that was about the request interface. Next, we have the DeNovo-based LLC. So let's talk about that. So this one, it supports the DeNovo states of invalid, owned, and valid states. In addition, it also supports the shared state to deal with MESI-style systems where you want shared copies of loads. The allocation here happens at the line granularity, ownership is at the word granularity, and the data field in the cache line tracks the owners of individual words. So there is no extra overhead for this tracking. And now this LLC could generate requests to the owners or the sharers, and for that we will talk about the next component. But here is just an example. So if the GPU is sending out a write-through and the accelerator is sending out a request for ownership to different words in the same cache line, with the MESI-style protocol, this would create false sharing. Not only that, it would create arrays, it would create transient states, it would result in blocking states, and lots of complexity. In this world, these are just simply two different words of the cache line, no problem. The Spandex LLC responds, and we are done. Okay, so no false sharing. There's non-blocking ownership transfer. It's just a very simple protocol. Okay, the next step is the external request interface. So to deal with some requests that might come from the LLC, the L1 caches of the devices have to support the responses for these requests. Now, this depends on what state the L1 cache already maintains. So the only thing that we need to handle here is, if you maintain the own state, okay, then you need to handle certain external requests. The GPU cache does not maintain own state, doesn't need to deal with any of that. All right. DeNovo does not maintain shared state, so it doesn't need to deal with the rows here that require shared state. So the details of this are in our ISCA paper, but just to give you a little bit of a flavor, let's say that we have these three protocols here, and there is a request for valid state from GPUs. Well, it turns out the MESI protocol knows nothing about self-invalidations, so it doesn't know what to do directly with a request to a valid state. Well, just for this reason, we have a very thin translation unit that basically says, okay, I can deal with this valid state request, but I don't need to change my state at that point because the GPU coherence is not really stealing my ownership. Okay, so this is the only thing that this MESI protocol needs to do. This is the only thing that it needs to have a translation unit for to deal with these protocols. Okay, so very, very thin translation unit. So here is our evaluation. We use two configurations to evaluate. Our baseline is a hierarchical MESI. This is similar to what the AMD APUs do. The CPU follows a regular MESI protocol, and we have GPUs hanging off the network. The GPUs follow either our DeNovo protocol or GPU coherence. We have different versions for Spandex, where the CPU and the GPU are directly connected to Spandex, as is allowed by Spandex. And here, the CPU can be either MESI or DeNovo, and the GPU can be follow GPU coherence or DeNovo, creating 4 different configurations. Our workloads are workloads that use both the CPU and GPU from Pinotia and Chai benchmark suites. So this is execution time. The gray bars are the baseline hierarchical configuration. The green bars are the Spandex configuration. And the thing to take away from here, the first thing is really that different workloads prefer different protocols, right? That's the point of this thing. But the Spandex flexibility ensures that Spandex is consistently better than the hierarchical case. So the best Spandex is consistently better than the best hierarchical case. Okay, and there are, I don't have the time to go through more insight into why we get results like this, but again, the reason for different workload performance changes. So what this also tells us is the idea of mixing and matching different protocols is a good one, and that's what we want to do with Spandex next. Okay. So the network traffic, again, similarly much better with Spandex. So to conclude, we started off with multiple devices on a system. The standard way is to do MESI LLC, and we have developed Spandex so that we can integrate things much more seamlessly, much more in line with what the individual devices want to do. It gives us simplicity, flexibility, efficiency. And next, we want to go much further and exploit software or hardware hints about data access patterns to do further coherent specialization using a variety of techniques such as dynamic request selection for Spandex, producer-consumer forwarding, and much more extended generalized granularity of requests. So I will stop here. Oh, and then we want to use different accelerators and different memory structures. Okay, questions?
We now have time for 1 or 2 questions.
So there's the right ownership at word granularity. That seems a little bit orthogonal to the rest of the DeNovo or the Spandex protocol. Is there a quantification of how much of a gain that alone provides? Because that seems to have, that would have some overhead in your tags in your last level cache.
No, the overhead is actually very limited because the ownership tracking of who owns the data is done within the data banks of the caches. Because if somebody owns the data, you're not using the data field, right? So you just keep track of the owner there. So the only extra state you need is just that one bit that says, is this a pointer to the data or is it the data itself, which is really not much at all, right? And this is actually a key part of the DeNovo protocol. And it is a key reason why we get the simplicity and some of the performance benefits. So some of the workloads that I showed, the benefits are coming because we can do ownership, right? If we didn't, yeah.
Thank you.
I have a question. I have seen that you maintain the coherence between the block and the the word granularity. So have you considered to maintain anti-coarse granularity such as the page granularity?
So have I
more coarse granularity such
more
as
coarse than a cache line? You mean?
Maybe because the cache line is 64 bytes. Have you considered for 1 kilobyte more large one?
Yeah. Yeah. So that is actually the next step, the granularity part. So the other interesting thing is that because of this way the states work in these protocols, so you can see up here, if you have a producer of some data and a consumer, not only can I send at whatever granularity I want to, but I can send data directly from the producer to the consumer without going through the Spandex LLC. And the reason for this is that if nobody else is sharing the data, okay, the DeNovo cache doesn't need to know about any state transfers. Okay?
Thank you.
So, so it's even more than just the granularity. It's this direct, it's almost like a message passing system, but within the context of a globally addressable space.
Yes, thanks for the questions, and thanks, Sarita,